All right, so let's go ahead and get a brand new definition for acids and bases outside of our Lowry-Bronsted. And these are going to be just named after Lewis. This is the same Gilbert Lewis who actually got Lewis structures. They got a lot of stuff named after them. So a Lewis acid and a Lewis base is going to be kind of our broader version of our Lowry-Bronsted. I'll write that down. So kind of a broader, a broader version of our Lowry-Bronsted. And because of that, we have this kind of special kind of like relationship where all Lowry-Bronsted kind of acids, for example, are also Lewis acids, but not vice versa. So just because you're a Lewis acid does not mean that you're a Lowry-Bronsted. Lewis is kind of like super big and broad, and then Lowry-Bronsted is narrower, and then Arrhenius is like even more narrow. So this is kind of like the biggest, most kind of like all-inclusive version of a kind of a definition of an acid and a base. And you can actually get reactions which are acid-base where no hydrogens or protons are involved at all. So in terms of our definitions, and this is going to introduce two really important new terms. Our Lewis acid is going to be the acceptor of a lone pair. So when we draw our mechanism, we start at our base and then it goes towards the acid. That acceptor of the lone pair is kind of like where that arrow goes. And this is going to have a nice new term that we're going to use a ton, which is electrophile. Your electrophile is going to be your electron deficient or electron poor species, and is going to be the sink when we kind of talk about our source and sink. Your base is going to be the donor of the lone pair. That's going to be where the electrons are, and we're going to use this term of nucleophile. Nucleophile is going to stand for lover of nucleus, where electrophile is going to be lover of electrons. So your nucleophile is going to be your electron-rich species, and that's going to be our source. We're going to use these terms of nucleophile and electrophile for the rest of organic chemistry and the rest of your life in organic chemistry. That's just something that's never going to go away, and we're going to use that a ton when we're talking about like different types of reactions. So if we actually look at this kind of example above here, we have BF3 reacting with this diethyl ether to form this complex. And this is actually able to be described as an acid-base reaction under Lewis. In a Lowry-Bronsted, this would not count at all as a acid-base reaction, but under Lewis it is. So let's go ahead and think about what is actually happening here. If I look at my kind of like starting materials and my product here, I see one of the main differences is that there's a bond between my oxygen and the boron. And at the moment, these are two separate species. I have the boron and the first, and then the oxygen is the second. So there needs to be a way in which I get a bond that's formed between this oxygen and this boron. So here, I do know that my oxygen is going to have lone pairs. So this can serve as a Lewis base or a nucleophile because it's going to have a pair of electrons, our lone pair, that it can donate in order to make a bond. My BF3 is going to be my Lewis acid, and it is going to be our electrophile or the sink. It's going to receive. So in terms of my arrows here, I can show an arrow from my lone pair on my oxygen to that boron. This arrow right here is showing a making of a bond, which is that yellow one that we highlighted in our products. And we only have one because we're not actually abstracting a proton or anything to actually show that the formation of a lone pair. And here, instead, we ended up just with charges where that boron is now more bonds than it wants. Boron wants 3, it now has 4, giving it the negative formal charge. And oxygen wants 2, it has 3, giving it the positive formal charge. Now, one of our kind of questions might be, in the first place, Dr. Eck, why would the lone pair on the oxygen want to attack the boron? And that's actually going to come from something that we talked about all the way back in our first unit when we were thinking about our hybridization and geometry. So if we think of BF3, and let's just think of our boron. If I asked you what was the hybridization of that boron, with great confidence, I'm sure that you would tell me that it is sp2 hybridized. It has 3 domains, each with a fluorine. Boron is a moron, as we kind of say. So it's okay with just 6 electrons. So it does not have a full octet, so there is no lone pairs there. And with that being sp2 hybridized, I'll even go and write that down so we have that officially there. sp2 hybridized, we know that geometry is going to be trigonal planar. So we can imagine a plane, like a piece of paper here, where we have a boron and then all of our fluorines with 120-degree bond angle, all flat on the paper. With this, that does mean that there is one orbital which was not involved in our hybridization, and we'll often call this a pz orbital, and that pz orbital is going to be out of the plane. So here's our kind of pz, and I'll go ahead and just give a phase to one of them. That color doesn't matter which is which. And this pz orbital is going to be empty, meaning there is a sink where you can put electrons, and that's going to be one of the reasons why you will have this boron be attacked by that oxygen. So that's actually coming back from stuff that we actually kind of thought about all the way back in our first unit. So let's go and get some practice thinking about if our structures can be Lewis acids or Lewis bases. So in example 4 here, I have 4 different structures, and we're going to go through and think about whether or not this can be an acid, a base, or both under our definition for Lewis. So in our very first one, we have a carbocation. So we have a carbon that has 3 hydrogens around it and only 3. So it does not have 4 bonds, giving that a positive charge. If I'm looking at this carbocation, our question is, does it have lone pairs that can be involved in a reaction? Nope. It just has 4 single bonds, or sorry, it has 3 single bonds to hydrogens. Therefore, this cannot be a Lewis base. Now, can it serve as a Lewis acid? Can it accept? And yes, this positive charge is a sink in the same way as we think about our BF3 from the last one. If we had to describe the hybridization of that carbon, we would say it's sp2 hybridized, and that would be trigonal planar with that plus charge sitting kind of above and below that plane. So that is able to actually be attacked. So this can serve as a Lewis acid. What about water? If we draw water out a little bit more. So for water, we see that it has lone pairs. And if it has lone pairs, that means that it can be our Lewis base. It can use those lone pairs to go and do attacking. But it also has an H. And that H can be abstracted through our traditional Lowry-Bronsted. And if I'm a Lowry-Bronsted acid, I'm also a Lewis acid by that exact same definition. I can't go the other way, but I can always go like more broad. So this actually can also be a Lewis acid. So therefore, this is going to be both. So water can be both an acid and a base under our Lowry-Bronsted, as well as our Lewis. Now let's look at this nitrogen species. I have a nitrogen with 2 hydrogens bonded to a methyl. This is sometimes you'll see written as Me. That's our CH3. Here we have a lone pair. That lone pair gives us the ability to be a base, and I have an H that I'm able to abstract as a proton. So for the exact same reasons as water, this can be both. Now, if I made a slight change to this molecule, and instead of having this be an NH2, if instead I had, let's say, a nitrogen and a CH3 CH3, CH3, and then a lone pair. These hydrogens are a lot harder to actually abstract, and this one is really only going to want to be a Lewis base. Because of the fact that those hydrogens aren't going to be attached to a good electronegative atom. And we'll talk a little bit more about that in kind of future videos. Our last example here we have in number 4 is looking at AlCl3. And here we see that we have aluminum. And aluminum, if we look at the periodic table, is in our exact same group as boron. So it's going to be much like boron, meaning it is going to be sp2 hybridized and have an empty pz orbital. And that pz orbital can come and be filled, meaning that this will be a good Lewis acid in the same way as our carbocation and our boron species was. While there are electrons, lone pairs around those chlorines, my chlorine already has one bond. It has no desire to go anymore, and therefore this cannot actually act as a Lewis base, and it can only act as a Lewis acid. Arrows for Lewis acid base in terms of mechanisms are going to be super similar to what we see with our mechanism arrows for Lowry-Bronsted. There will be kind of 2 major types of arrows. The first one are going to be ones that form complexes, and a complex is going to be kind of example like we saw here. We would call this a Lewis acid base complex. Here we don't get our conjugate acid and our conjugate base, we just get a single compound, so we don't actually use that kind of like nomenclature. Anytime when we get a Lewis acid base complex, that is going to just have a single arrow that's going to be from our lone pair to our species. So for example, if we wanted to show maybe a different one, we can maybe show with some of the ones above. If we show our structure that can be both attacking maybe our aluminum chloride, which can only be an acid, we can show a curved arrow going from that nitrogen to that aluminum. This would form a complex, so I only have one set of arrows. That's one kind of like slightly unique thing that you'll have in the Lewis acid. If instead we're doing just like a traditional structure, like maybe we have the ones that can be both, let's draw that exact same structure, CH3, HH, and lone pair. And let's just go and react this with water. Be a little bit boring. This can come, abstract a proton, and then make your lone pair on your oxygen. This would fit our traditional kind of like Lowry-Bronsted, where you do have those 2 sets of arrows. So there is a possibility in your case of your Lewis acids that a complex is formed rather than a separate conjugate acid and a conjugate base. And instead of having those 2 arrows that we showed in our last video, we have just a single arrow to form our complex. And that's just going to be from our base, which is going to be our source of our electrons, to our Lewis acid, which is going to be our sink. We'll go ahead and stop our video there, and then in our next one, we'll start talking about pKa's and kind of like getting values to actually rank how strong or weak something can be as an acid or a base.